$16.50. There we go. If I have 2 toppings, how much? $15. If I have 3 toppings, $16.50. If I have 4 toppings, $18. Then I'm out of room on my graph. Is this discrete or continuous data?
Continuous data.
I can have half a topping? No. So is this discrete or continuous?
Continuous.
It's discrete because I cannot have an input between 0 and 1. Right? If it was continuous, I could put on 0.25 of a topping, go up here, and get a price. Can I? No. So this is discrete. First thing, that's from yesterday. Now, next, what do you notice? As I go 1 this way, how far do I go up? 1.5. As I go 1 this way, how far do I go up? 1.5. 1, 1.5, 1, 1.5. Creating what? A little staircasey looking thing. That's the same every step, right? That fact that the rate of change, which we've already talked about this unit, is constant, means that this is what we call a linear relation. Because a linear relation will always follow that pattern. Now, notice I cannot draw a line here. So even though the word line is in linear relation, I know it just went blue. Even though line is in the word linear relation, you need not have an actual line. It is not the line that makes a linear relation. It is this rate of change. Does everybody understand? All right. Remember when we drew a graph that looked a little like this yesterday? Was it a linear relation? No. Because the car changed on the 3rd day, didn't it? 165, 165, 165. Linear to there? Yes. And then 130. Linear anymore? No. Everybody good? Excellent. So now you have seen 2 ways that you can express a linear relation. One is with a graph. It makes a line and you can draw a little staircase. Now, just to make sure you actually understand this, is it just as valid for me to go that way and down? No. Either one. Could I have made the same blue dots going up and right instead of right and up? Yes. Now, so all of you have seen, I've told you you've seen 2. One is drawn right here. What's the second way that's on the screen, not on your paper, on the screen right now to show a linear relation? Words. You can describe a linear relation. You can draw a linear relation. Is everybody cool? All right, now we have to dig back into our brains to the 9th grade. I know it's a long trip, but I think you can handle it. The other ways you can show a linear relation are a table of values. You people probably call them T-charts. That's a new phrase for them that has come about since I've been teaching. So apparently I've got to change my wording. I had never heard of it either until like 3 years ago. I don't know, but whatever. In grade 9, we had X and Y, correct? In grade 10, what did those change to? Input, output, or better? Domain and range is the whole set of them, but you're all on the right track. IV, DV. Right? Everybody's cool with that, yeah? Okay. Tomorrow there's going to be another change to that, but that's cool. It's all still basically X and Y. So, in our linear relation, my independent variable was toppings, correct? So if I had 0 toppings, what did I pay for my dependent variable? $12. If I had 1 topping, what did I pay? $13.50. 2, 15, 3, 16.50. Now, to show linear relations on a table of values, you must check and see if those changes are always the same. How big was that change? Plus 1. How big was that change? Plus 1.5. Can you prove a linear relation with only 2 points? No, because you can always connect 2 points with a straight line, right? So you need at least 3. So we're going to check once more. Plus 1. Is that cool? And then plus 1.5. Is it linear? Okay, now, see if you really get this. What if I told you this one was 5? What would this be? $19.5. Why, Tiana? Because my jump was now the plus 1, but I jumped 3 times, right? So my 1.5 must also have jumped by 3. Is everybody good? So even if it doesn't look linear, you should check that it's linear. Does everybody follow? Because if I only put in those 3, most of you would say that that is not a linear relation. Because you would say plus 2, plus 3, plus 3, plus 4.5. Most of you would say that's not linear. But you know that it is linear, don't you? Everybody understand this? Okay. So that's the third way with the table of values. Now there's a fourth way with an equation. Now that equation works in 2 ways. Now I'm going to write them both over here. So the first one was cost. No, not cost, sorry. The first one was topping cost, right? So it was 0, 12, 1, 13, 50, 2, 15. That's good enough. Now, our equation is always this. dV equals IV with some math. Always. So, in this first method, what's happening here? I'm adding 1.5 and adding 1.5, correct? I am repeatedly adding 1.5. Is there a mathematical shortcut to plus, 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 plus? Multiplication, right? So my dependent variable is going up by plus 1.5 plus 1.5, right? My dependent variable depends on my independent variable, doesn't it? So my independent variable must be multiplying by 1.5 to equal my dV, correct? Everybody's with me? All right, now let's check. My IV in this first line is what? 0. What is 0 times 1.5? 0. But I need it to be 12, don't I? I heard, but I left it alone. No names. It's a safe space. Right? Okay. Don't worry. You're not the first person today to say that exact same thing. So, what did I need this to equal? It needs to equal 12, doesn't it? So do I need some more math here? What is the more math that I need? You do. How do I get from 0 to 12, Jacob? I add 12. That's it. So my equation is cost, my dV, equals toppings times 1.5 plus 12. Everybody cool? Now, some kids understand how to find an equation using this gold version. Not everyone does, so I like to show a second way to do it. All right? But it's the same thing. Toppings, cost. 0, how much do I pay? 12. Everyone agree? Okay. If I put on one topping, do I pay that same $12? Yeah, I have to pay 12, don't I? But I have to add how much more? 1.5. Right? Okay. If I put on 2 toppings, do I pay that 12? But now I have to pay 1.5 how many times? Twice. If I get 3, what do I pay? 12 plus 1.5 times 3. What if I put on T toppings? 12 plus 1.5 T. Does everybody understand one of the 2 ways to find an equation from a chart? Everyone is good? All right. In this box down here, what are the 4 ways to make a linear relation? What's the first one? Words. What's the second one? A graph. On a graph, how do you know it's linear? Constant rate of change. Now, if that doesn't mean anything to you, what was the word you all used? Staircase. The third way is a table of values. I'm running out of room, so I'm writing T of V. How do you know it's linear on a T of V? What happens to the x's? If they go up or down? Yeah, right. Same change on each side. And the fourth one is just an equation, which grows right from the table of values. Everybody cool with linear relations? All right, let's put it into practice. Turn the page over. There is your very first table of values. Is 2a linear? Why? Plus 5, plus 5, plus 5. We're halfway there. What's that one? 9, 9, 9. All the same all the way down? All the same all the way down. If I went to 25, what would the next one be? $77. Because I did 2 jumps there, so I'd have to do 2 jumps there. Is everybody good? Excellent. This one, what's that change? 5. What's that change? What's that change? Am I halfway there? Yeah, it looks linear. 75. Oh! 2,925.
What?
Is it the same?
No.
So no, non-linear. And this one was linear. All right. Uh-oh, I've got an equation all of a sudden. Can an equation tell me if it's linear? Yeah, there is a way to do it, but do you know it? So what should I do instead? How do I know if it's going to be linear? What do I know works? Graphing it, checking for the staircase, or a table of values, right? Okay, well, what should we do? Table of values. Table of values are made up of x and y in grade 9. We've got x and y's here. Let's just use them. How many points do I need to use? At least how many? 3. Can those points be random? No. They should be a set distance from each other, yes? Who chooses the points? You do. Where do you put those points? X or Y? X. Why do you put them in X? There's an X in the equation, but better answer, because X is the independent variable, yes? And that is the input. Who does inputting? The operator. Me. Google will not search for stuff for me until I input something for it to search. Right? So I am going to choose 3 numbers. I'm going to write 3 numbers. You tell me if it's okay to use them or not. 1, 2, 7. Is that okay? It will work. Will it prove me linearness? No. Good. Why not? Should be going up at a constant rate. -2, 0, 2. Is that okay? All right. So -2 is an X. What do you see right there? So I have 2 times -2 plus 4, which equals what? 0. So what would be the point on the graph there? -2, 0. Nicely done. What's 0? 2, 0 plus 4. What's that? 4. What would be the point on the graph? 0, 4. Holy crap, look at you guys. 2, 2 plus 4. What's that? 8. What would be the point on the graph? 2, 8. My good gravy. What am I going up by? What am I going up by? 4, 4. What if the next one was 3? What would the y value be right away without doing any math? 12? Really? I went from 2 to 3. 10. Because I went half as much there, so I got to go half as much here. Does everybody understand? Sweet! Now, what do I got there? Another equation, right? So I'd better check it. Can I use -2, 0, and 2 here? Sure I can. So that's going to be 4 times -2 squared minus 1. What's that? What's -2 squared?
4.
Times 4?
16.
Minus 1? 15. Aye. 0. 4 times 0 squared minus 1. Hey, what's 0 squared, Karen?
0.
What's 0 times 4, Karen? 0. What's 0 minus 1, Karen? 0 minus 1, Karen? 0 minus 1, Karen? 0 minus 1. -1. Don't worry, I'll edit all that out. I did put her on the spot. But she kicked ass in the first 2 that she made a mistake on her. Oh, damn it! Beep! 4 times 2 minus 1. 2 squared. What's 2 squared? Times 4? 16. Minus 1? 15. Hey, wait a minute. Plus 2, plus 2, minus 16, and then plus 16. Not linear. That's something you're going to learn in grade 11. Now, what do you notice is different about those 2 equations? Because they look pretty similar. The exponent. Well, you were right too, but he said exponent before I was able to talk to you. The exponent is what changed it. An exponent means it can't be a straight line because exponents multiply, right? Okay. D, linear or not? How do you know? Oh, I think you do. There's a point right there, yeah? So if I go over 1, I go down a little bit more than 1, don't I? What if I go this way 1? Then I go up what? Little bit more than 1. Are they the same? So is it linear? What about this one? Linear. Why? Because it's straight. The change is constant. It doesn't change at all. Every time I go 1 to the right, I go up 0. 1, 0, 1, 0, right? So it's linear. Now, before we go on, what is the equation of that line? It's y equals 2. Absolutely correct. Weird, though, because everybody wants to say that it's x equals something because it's going sideways, right? But it's y equals 2. Turn the page over. Linear or nonlinear? Nonlinear. Because the change is different, right? When I go over 1, I go up 1. So when I go over 1, I should go down 1. Hey, there's nothing there. It's way down here. So not linear. And scribble, scribble. Linear or nonlinear? What's its equation? Oh, you guys, you're on fire. I got to be careful today. Whew. Make a table of values and graph. X, Y. How many dots do I need to make an efficient graph? 3. Should I choose 3 that are right beside each other? I can. That makes it a little hard to graph, especially if my graph paper is tiny, right? Tiny graph paper. So I'm going to make it a little bit bigger. I'm going to go negative 2, 0, 2. So what is this? 2 times negative 2 plus 4 to get 0, which gives me what point on the graph? Negative 2, 0. What's 0 get me? So what's the point on the graph? And what does 2 get me? So what's the point on the graph? 2, 8. Let's graph it. Negative 2, 0. 0, 1, 2, 3, 4. And 2, 1, 2, 3, 4, 5, 6, 7, 8. And that makes a nice line. Where's the next dot going to be on the left? How will I find it? I went 2, 4. So how will I find it here? 2, 4. Where's the next one going to be? 2, 4. Where's the next one going to be? Off the graph. So we could stop. Everybody understand? What's the next one going to be to the right? Off the graph. Could I go 1, 2? Yeah, because it's the same thing. Is everybody good? Sweet. Could you go 4, 8? Could you go 12, 24? Could you go 32, 64? Could you go 128, 256? Good. What about this guy? How many points do I need? 3. Let's use good old negative 2, 2, 2. What's negative 2 squared minus 3? 1. So what's the point on the graph? What's 0 squared minus 3? 0 squared minus 3. You guys. What's the point on the graph? 0, negative 3. What's the third one? So what's the point on the graph? Graph it. Negative 2, 1. 0, negative 3, 2, 1. Now, how would we graph that? What do you want to do with these 2 lines? Or these 3 dots? Connect it. Right? And right. It's a V? Would it be a V? Isn't a V linear? No. Over 2, up 4. over 2 up 4. Those are making straight lines, aren't they? So it can't be a V. It is a U. How would you prove it? Check another point. What happens if I put 1 there? What's 1 squared? Minus 1? Or minus 3 is negative 2, right? So 1, negative 2. So the other one would be at negative 1, 2. And there you can see it goes over 1, up 1, then over 1, up 3. So it's curving. This is what's called a parabola. You will see those next year. A crap ton of them. In any math you choose to take, you will be dealing with curvy lines instead of straight lines. Everybody good? All right. You need to work on page 168. The work ends on page 170. Now listen to me carefully. Tomorrow you're going to get that quiz. You're going to get a lesson. Okay? That lesson, 5-5, comes with work. In a perfect world, I will be back here Friday to teach you 5-5, and you will take 5-5 home for homework over the weekend. I will be back here Friday to go over 5-5, because the TOC in a perfect world will teach it to you tomorrow. He will teach it so well that you guys are ready to go on and do your review on Friday. If I don't get a math teacher, I get a second grade music teacher who says, letters and math? What are you talking about? That's crazy. Then you will just see the notes and you will try to work it out. All right? Everybody with me? Okay. If that happens on Friday, I will obviously go over 5-5, and you will have more review homework over the weekend. If it's a math person tomorrow, you should have the whole period on Friday to work on your review. So you should have no homework. Everybody cool? All right. And you've got, look at that, 20 minutes left in class to get this homework done. Stop it, Mr. Myers. You're so nice to us. I can't believe it. Oh, and I'm still recording. What are the chances of that?